Hi, good afternoon everybody and welcome to this joint webinar between Innovyze and Hydro International on meeting greenfield runoff rates using complex controls. For those of you who are just joining and are new to GoToWebinar, you'll see that there's a chat function down at the bottom and also questions. Feel free to raise and ask any questions throughout the webinar as we go along. And we will generate an FAQs sheet. We'll try and answer as many as we can as we go, but we'll also be sending out a link both to a recording of this webinar and also to an FAQ sheet as we go along. So first of all, let's start off with a couple of introductions. I'm delighted to be joined today by Chris Newton. So I've got Chris with me. Chris is the Regional Technical Manager for Hydro International and is an expert when it comes to all things flow controls, in particular those hydro brakes that we'll be seeing later today. And for those of you that don't know me, my name is Max Anderson. I'm the Product Manager at Innovyze for MicroDrainage. So I'll be speaking to many of you in regards to how to use the MicroDrainage software and how to get the most out of the software. So we've had a really good response and great take-up to this webinar, so hopefully we're doing something right, and it's quite a pertinent topic in terms of these complex flow controls. So great to see so many of you joining us today for the webinar. To give a bit of a scope of what's going to happen as we go through then, we'll discuss these greenfield characteristics, some of the theory and regulation behind why we might want to look at implementing complex flow controls, and Chris is going to talk to us about that, and then also how we actually achieve multiple discharge rates through the use of flow controls like the hydro brake and the different sorts of arrangements that we can use when designing complex flow controls. What we'll then do is, after Chris has given us some of his thoughts, I'll then show you how we actually go about the design of complex flow controls in a real MicroDrainage project. We'll also do a bit of a comparison of our storage volumes against Q-bar and the impact that being able to hit multiple discharge rates enables us to do. We'll draw some conclusions out of that, and we'll also discuss some upcoming events. And for those of you as well, if you're used to the format of Innovyze webinars, you'll see, if you keep watching to the end, you'll see your password for the CPD, which will be coming to you via the survey link that will be emailed out at the end of this webinar. So without further ado, we're going to get going by asking a couple of questions. So we're going to go through and ask you a couple of questions at the minute. So if you could just respond to these and tell us some of your thoughts. We're going to start off with, have you avoided designing complex flow controls in the past? So yes or no's would be really interesting to see the responses here. I know it's one of those that sometimes people have often felt it's a bit of a mystery, the way that complex flow controls work. So it'd be really interesting to see the results of this one. So just give it 5 more seconds now. Great, good to see a lot of you have voted. So we're going to close the poll now and show the results. So interestingly, there we go, 51% of you, yes. So if you've been hiding away from designing complex flow controls, and perhaps with a couple of good reasons. So we're going to ask you another one, and we're going to see why it might be. What's your biggest concerns when designing these complex flow controls? So hopefully you should now see the second question on there. So hopefully, yeah, you can start to fill that one in. Again, we'll give it a little bit of time for you to get your responses in. Okay, yeah, looking like an interesting set of results. 2 clear front runners at the minute. Okay, so I'll show you the results. So yeah, this is quite common, certainly in my experience. It's either been too time-consuming or complex to do, or just a general lack of I'm not quite sure how to do it. So hopefully that rings true. Chris, similar in your experience?
Very similar. I was surprised the prefer to design for long-term storage was as low as it's come out.
Yeah.
It's usually a bit higher.
Okay. Right. We're gonna ask one final question then, and then we'll get going in the webinar proper and see if we've been able to do our job come the end of it. So, in regards to this, when we're looking at the alternative to designing to Q-bar rather than our multiple discharge requirements, is this something that's sort of common practice? And would you actually say you default to it, really? Sometimes we have no option if we've got site conditions that mean we're not reducing our volume sufficiently. Then we may be held to Q-bar in any regards. But where we have a choice, yeah, interesting to see this. So we're just going to click that poll as well. And again, yeah, so quite a decent split there in favour of yes. So yeah, and again, I think that is quite common. So hopefully we're going to be able to do something about that now. So where you can hit those multiple discharge rates, we're going to give it a go. So well done, team. We've got the team here running the polls, so thank you very much for that. And I'm going to hand over to Chris now, who's going to give a bit of an introduction to complex flow controls and their design.
Afternoon, everyone. So my little introductory bit is going to go over talking about the flow controls, why they're used, different ways in which you can use them, and then start to sort of introduce the concept of tackling what different head levels that you need to target or could target, and then just close out with a little comment about operation and maintenance of those flow controls before I hand back over to Max to go through the demonstration. So flow controls and storage are very much intrinsically linked, and depending on the type of flow control you select, that can have a significant impact on the volume of storage that you have. And it's not just the top design flow rate or your peak design flow rate that you're designing for, which will have an impact on that. The storage is also very much defined by the behavior of that flow control as it builds up to your peak design flow rate as well. So comparing vortex flow controls and orifice plates, because of the behavior is different, that can end up lead between a 30% to 15% increase in your storage volume that you might have to then hold on site. So complex flow controls have been talked about for a number of years now and started coming through the non-statutory technical standards for England and Wales a number of years ago. These are still non-statutory for England, and as Wales are implementing Schedule 3 as of January next year. But this talks around two areas of controlling the peak flow rate that's coming off of your system, specifically for the 1 in 100 and for the 1 in 1 year flow rate. It also talks about volume control as well, and holding an amount of volume on the site for your 1 in 100 year 6 hour rainfall event to therefore try and mitigate the potential flood risk that can happen downstream because we have more flow coming off of the system. And this comes around because that we changed the way in which the system is working. So complex flow controls only have to go onto new build sites, and so it's typically where we're changing a greenfield application or behaviour that's on the left, where we have a significant increase in the amount of evapotranspiration coming off the site, increased amount of base flow coming off because the water that falls onto that site infiltrates into the ground, but little amount of surface water. So as we then construct on the site, that flow behaviour and characteristic running off the site changes, and we have that increased amount of surface flow coming off of hard standing areas that can therefore cause that change in flood risk and potential flood issues further around the site and downstream in existing areas. And so what we're trying to do with that complex flow control idea is take the built environment and built flow coming off of the site back to what that sort of greenfield behaviour was, and reduce that surface flow to a suitable level. Historical number of customer concerns and issues with the designing complex flow control is shown on the screen, very much similar to how what has come through from the poll questions just a moment ago, which shows that concerns and issues for staying quite static at the moment over time, but hopefully this webinar will and some of the tricks that we can show you can help demystify some of that. But after the webinar, if you have any more questions, we're more than happy to try and demystify this a little bit further for you if required. So different ways that you can achieve complex flow control. There's options for doing it with either one flow control or multiple flow control. One flow control options, typically penstocks and gates, end up being movable and mechanical devices in which maintenance and operation of those is a little bit more extensive. You're sometimes lucky enough to be able to do achieve complex flow control with one flow control using orifice plates for vortex flow controls if your flow rates and head levels line up quite nicely. But typically you end up having to go down the multiple flow control route, and that's where you're putting multiple flow control units into a chamber or in multiple chambers. And this can either be done in whether it's series or parallel. So the more common scenario is where you do it in parallel. It's a more space-saving application in which you put multiple flow controls on a weir wall. And so example Max will be showing you later goes into that. And that's where we then are summing up the characteristics of flow controls and adding up the amount of flow that comes through the system. Sometimes it can be more appropriate, however, for certain sites is to start having them in series, especially if you have large increases in the amount of flow that is going to come through the system, say from your 1 in 1 year to your 1 in 100 year. And this is where we end up drowning out the smaller first flow control with a larger flow control. And so you end up with sort of characteristics as shown below, where the one on the left shows you sort of sum up the flow controls on top of each other and the amount of flow that's coming through at the various head levels, and the unit on the right showing where we've had a smaller flow control in operation and then it's drowned out and the larger flow control starts taking effect and controlling the flow instead. With regard to sizing flow controls and with the way in which the built environment now works is that we start looking at having smaller and smaller flow control discharge rates that are coming off of the site. And this is starting to come through more and more in legislation with lead local flood authorities, but is also now being shown in the upcoming Sewers for Adoption 8 in the pre-implementation edition that's already been published, but it's due to be becoming live as of April next year. And so this selection of text from the document is covering the design of flow controls specifically for surface water designs, and so we have two different minimum opening sizes that we might want to target depending on the amount of debris that's coming through the system. So open culverts, open channels where there might be large amounts of debris that's being collected, they suggest a minimum opening size of 100 millimeters, which is very much standard to what has previously been there and the common selection of using a 5 litre per second flow control. But where you're looking at closed systems and you've got a reduced amount of debris coming through the system and a very much reduced likelihood of flow control being blocked, we can start going down to that 50 millimeter outlet diameter to therefore look at reducing that flow rate off-site. And so this graph just compares two flow control designs, one being the Hydro-Brake Optimum, where we've set the unit to have a minimum upstream storage design, and a Hydro-Brake orifice plate, in which both units have a 50 mm outlet diameter, and then the two curves show what the flow rate and head level design points that can be achieved. So for a 50 millimeter outlet Hydro-Brake Optimum, the minimum flow that we can have coming through the system is just below 0.8 litres per second if it was around a 0.3 metre head. And comparing the 1 metre design head level for a Hydro-Brake Optimum, you can end up with just over 1 litre per second design flow rate coming through the system, as for an orifice plate you're just over 5 litres per second. So you can start reducing that amount of flow and therefore potentially not have to do any construction work downstream from there to mitigate flood risk levels anywhere else. But with selecting head levels are typically one of the more challenging bits of the design to tackle. Flow rate is very much an easier kettle of fish with regard to the design flow rate is typically either given to you or there's different methodologies that we can go through and look at selecting that, which Max will show you in a minute. But head levels, there's different scenarios in which different head levels we want to achieve based on good practice. So one of them for your 1 in 1 year, depending on the slope of your pipe, you don't want to surcharge the pipe network. But then for larger storms, say your 1 in 100 year, or say your 1 in 200 year, maybe using areas outside of the pipework may be much more appropriate, and designing for exceedance goes into a lot more detail about where you could start holding water, especially in sort of those above ground flow corridors where they are. So different examples of structures where you're going to be holding water and determining what head levels are. Surface water attenuation structures such as ponds, depending on how deep your pond is and depending on the gradient of your catchment, you're going to have to model that that chamber a number of times just to have a look at what the volume is that is capable in there, and then designing what those head levels might have to be. And that will sometimes be determined by what slope, side slopes on the pond that you have and the depth that is available. Subsurface attenuation structures, again, we don't want to surcharge the pipework, but typically to try and reduce construction costs, typically that attenuation structure will be sized for your 1 in 30 year flow rate at a minimum. So therefore, using above ground areas or maybe the roadway for your larger storms where appropriate to not flood people's houses or cause danger to life. Maybe having a design head that's above cover level might be appropriate to therefore control the amount of flow that's going through the system and make use of the topography above ground. And with pipe networks, again, sewage for adoption goes into a number of those points discussing how much water you can hold in pipework. But again, oversizing pipework around the catchment and what the cover levels might be will then end up determining what head levels that you are available. And lastly, just to comment on operation and maintenance, this typically comes up in conversation with regard to flow controls and having multiple flow controls in sections. The text on screen is, again, outtake from Sewers for Adoption 8, where it's the type of maintenance and required activities that you need to comment on when you're putting a plan together and putting a proposal for flow control design in as part of your design. And we've just answered some of those queries with regard to what, say, flow control maintenance that we suggest to try and mitigate some of those issues, to try and then help them go through planning. And once the site is built, frequencies for maintenance should be made monthly to 3 monthly, then 6 monthly for the longer term. Chambers should always be clear of debris every time that you go and visit. You visually inspect for signs of damage and check moving parts, and removing dirt and foreign substances from the internal parts and external parts of the unit to then try and make them make sure that those other bodies don't come and cause an instance. An installation of them does have an impact on how well these units work. Again, the picture on the right shows for a conical unit good installation, and that where we take account of how the unit performs and what debris is coming through and maintaining significant flow velocities coming through the system. Cheers. And on that note, we'll hand back to Max for the demonstration.
Fantastic. Cheers, Chris. So we're going to start moving into a real-world sort of example of this, but really interesting to note some of the points there in particular the use or the ability to start thinking about those smaller flow control rates as well, that a lot of people tend to be bumping up to the good old 5 litre per second minimum discharge rate. And interesting to see now how we can utilise a larger head and control the flow even more with something like a hydrophilic optimum, which is going to enable us to get a better understanding where some of our greenfield rates are down at that really sort of lower end of the site. It is now achievable. And that's going to be the first problem that we're going to look at. It is the determining those greenfield runoff characteristics. So Chris has already talked about some of the theory there. We're not going to, or we're trying to limit any increase or prevent any increase to flood risk as part of the development. And that means that our post-development discharge characteristics, both in rate and volume, need to be designed to either match or try and improve upon current conditions or our greenfield conditions. It may be that it's not necessarily greenfield, it could be pre-development. So you often hear the sort of pre-development conditions as well. We're going to do this. One good source of information is the Serious Sods Manual. In particular, if anybody's read the chapter on runoff in chapter 24, you'll see that there is a proposed table of runoff estimation methods that we're going to be looking at in here. And just to point out that we'll be using for ease the IH124 for greenfield site. So again, MicroDrainage is equipped with a lot of these different capabilities to be able to do runoff estimation for you, both greenfield and brownfield, within the software. So at this point, I'm going to move now into MicroDrainage, and we'll take a look at the project that we're going to start to walk through. So what you'll see, or hopefully everybody can see on my screen now, is that I've got a project that we've already started to go to some level of detail in specifying the drainage design network, and I'm interested now in controlling or determining those greenfield runoff rates. And to do this, I can open up a little calculator within the source control module of MicroDrainage. So you will all have access to source control on your licenses, and you'll find that there's a whole host of greenfield runoff characteristic calculators built within there. But in order to do that, I also need to have an understanding of the drained area of my site. So this, you'll see from the imagery, it is a completely greenfield site at current for this new development. So I'm going to be using greenfield with no urbanisation across the site. I'm going to start a new rural runoff calculator. Oh, it's actually got some data preloaded in for me. But if we have a look in the MicroDrainage model, under the results form, I can get a summary of the areas that have been defined into the network. So this is quite useful for me to get a quick eyes on as to, well, what is the area that needs to be drained or that has been designed to be drained. And I can see in here I've got the gross area, so this is all the area that I've either cut off that I need to consider in my drainage network, or that I am considering, not necessarily just the impermeable, but other areas that are also going to be contributing flow into the network. I can see I've got 6.532 hectares, so that is what I'm going to use. That is the total area that I'm draining, and therefore that is the area which I need to see the characteristics for in my runoff calculation. So what we've got is the rural runoff calculator within source control. We've got a whole host of different theories, including the REFH2 methodology that we can use. But today I'm going to stick to the IH124 methodology, and in specifically the interim code of practice for SODS recommendation of utilising the IH124 methodology, but scaling it down where we're dealing with areas of less than 50 hectares. So this is a pro-ratering of the 50 hectare result back down to the areas that we need to see, as was proposed in the interim code of practice. So I've put a return period of interest. This doesn't particularly matter because I'm going to see my Q-bar rate and my Q1 1300 year rates are going to be provided for me as well. I've entered my area. I've also got information in here about the average annual rainfall on the site and the soil. Again, these have come from the Wallingford procedure mapping that I can select and get parameters within the UK and Ireland for this. And I've also got growth curves to be able to get to those different return periods. And again, I can pick the most appropriate one. Here we're envisaging that the site is here in Wallingford, where we're speaking to you from today. I can calculate this, and what you'll see is I've been able to develop my different rates here. So I've got my Q-bar rate, 25 litres per second, but you can see that if I'm allowing parity, getting all the way up to sort of my Q100-year rate up there, then obviously I can discharge more water, I can discharge at a greater rate and reduce my storage volume. So that first slide that Chris was talking about, inflow against outflow, determining a storage volume. So I'm going to take note of these rates, and we're going to just move back to the presentation where I've recorded these. So I've got my multiple different discharge rates in here that I've been able to grab through. So I'm going to be looking to design a complex flow control to satisfy these three different flow control rates. But first off, I need to consider where I'm putting it into the model and how I'm going to be considering this model. So first of all, let's take a look at the flow control chamber. So it's typically going to look something like this. As Chris mentioned, I'm going to go for a parallel approach. So I'm going to be designing with flow controls in the same chamber to one another. If you wanted to implement a series approach, then I'd just do that in MicroDrainage by dropping flow controls on different manhole locations, so maybe 2 consecutive controls, and we could design each control separate from each other and then look at their combined behaviour to ensure that we're achieving a series approach. We're going to do a parallel one though today. So it's all going to be based around my desired upstream head. So the head on the upstream side of the flow control is going to often be critical to designing this. So we've got the flow rates, we need to consider appropriate heads. And we've got a couple of things that can help us with this. The first one is going to be to look at a Q1 rate. And you'll know in the 1-year event, or maybe 1 in 2 year or 1 in 5 year return periods, we're looking to have no surcharging of the network. Well, surcharging is all related to soffit level of the pipe. So I can use soffit level of the pipe here. I'm using a 675 mil pipe. That's going to determine my allowable head, my maximum allowable head in the 1 in 1 year condition. So I can design my first flow control subject to a head to give me an outflow. So here in this example, looking at a head level, and I'm going to get an outflow in comparison to that. The second level may be related to a safety factor. So for example, if we're designing a pond, we may have a maximum depth available within the pond of say 1.5 meters for my 30-year rate, or perhaps if I've got the no flooding in the 30-year, it's going to be my cover level. But I'm going to reserve my cover level for my 100-year event. I'm going to say that we're not allowed any flooding on the site in the 100-year event. So I'll use my 100-year level as the cover level, and 1.5 meters is going to be my 30-year maximum depth in any pond that I'm developing. If we look at a secondary water level though in the design, what we have to consider is that any second head, irrespective whether it was our design head or not, it's going to change the amount of flow through the flow control. And this is the point that Chris was making earlier about the fact that we may actually be able to hit multiple different discharge considerations using a single flow control. So I'll show you how we have to consider that and why we need to be careful about that as we go through the design of our complex flow control in a second. But just to show you, subject to a different head, we get a different flow. We're only using one flow control that's active at the minute. If I subject it to a third head, so an increased level of head, then what I have to consider is I now have a head of H3 acting over flow control number 1, and therefore I get some flow coming out through flow control number 1, but I also get the difference between that invert level of the second flow control and the top water level, the head level, so H3 minus H2 in this example, acting now through flow control 2. So just to look at the fact that our outflow is now, it's a cumulative effect of flow going through flow control number 1 and flow going through flow control number 2 as well. So I'm going to bear that in mind when I go into the software and see how we can do that within MicroDrainage. So moving back to the network model and looking at plan, you'll see I've actually already identified the flow control chamber that I want to implement this in. And I've used a neat little feature within MicroDrainage, which is something known as the design flow for the pipe. And I've set that to 80 litres per second. And that's because I know that designing this complex flow control, this could take a while. This could actually be an individual task for somebody to go away and consider this. So I've still got some downstream pipes that I need to be able to design. But rather than design based off intensities, I know, because my Q100 year rate is 79.9 litres per second, or near enough 80 litres per second, that my downstream pipe from this flow control chamber is only ever going to have to deal with 80 litres per second of flow. So I can size my downstream pipes using a design flow. So you'll see I've just, in the properties of my pipes, I've added in a design flow in here, and therefore my pipe will be sized appropriately. This allows me to downsize pipes behind flow control chambers and can really speed up the process. So someone was able to complete the design of the pipes and attenuation network. I'm going to come in now and do the slightly more complicated design of the complex flow control into this manhole S10, my flow control chamber. So to do that, I'm going to be placing an online flow control. It's controlling flow moving to the next downstream element. So it is an online flow control, so I'll open up my online controls form, and for many of you, you'll be familiar with what we have to do now. We have to tell MicroDrainage where in the network we're going to locate this flow control. So at this point, my downstream pipe is going to be 1.022, and I need to select my control type. So when we're coming to do the complex flow control, I'm going to go down and select the complex option. It's always the last one on the grid, and what you'll see is MicroDrainage is already picking up some intelligent information from the model. So it knows the invert level of the chamber, it knows the cover level of the chamber, and it's assuming that I'm placing the invert level of my complex flow control at the very bottom of this. And what you'll see is I get a depth versus flow relationship, but crucially I've got an edit button in here, and this is where we need to go in and we're going to start looking at each constituent flow control in turn. So I'm going to open up this complex control form, and what you'll see is that I can start to add in different constituent flow controls to the model. So we're going to start off by using a hydro brake and considering that first condition. Okay, so what I could do is I could go through and specify my depth above invert, and invert here means reference invert level of the control. So in this case, I want that to be 0. My bottom control is going to be at the very bottom of my flow control. This one will always be 0. I could put in my design head and my design flow. I could specify everything beautifully in here, but actually the trick to using complex flow controls is I'm just going to extend this little option here, and I get 2 extra columns on here, depth and flow, and what this relates to is cumulative depth and cumulative flow through the flow control as we go through, and this is going to become really important. You'll see it actually starts to grey out some of the positioning and design head and design flow parameters, but that's fine. So I said a minute ago that we're going to set our design depth to be the soffit level of the pipe in the 1 in 1 year condition. So I'm going to go for 0.765, and I'm going to specify my first flow rate, which was the Q1 rate of 21.3 litres per second. So I can now click solve, and MicroDrainage will go and, using the Hydro International calculator, define the hydro brake that I need to use in this circumstance. So I can see I've got one that's now been designed to hit my design point, and it's now just a case of starting to build up the complex flow control. So again, don't worry too much about the depths. We're going to be telling it the depths, and we're going to use in a minute some of the optimizing options to make sure that we hit those depths. Normally we've sort of got a simultaneous equations in 3 variables, if you like: depth, flow, and the shape or size of any storage structure. So what I'm trying to do now is I'm going to reduce the problem down to just needing to worry about the size of the storage structure later on. But I know that for a lot of you, it's balancing all 3 of these things. But what I'm going to do is I'll add in the 30-year one now. We said that we're going to try and keep, if you like, a minimum depth in the 30-year case of 1.5 metres, and my rate was 56.7 litres per second in this case. So now that I'm adding in the second control, I'm going to click Solve. And what MicroDrainage is doing is it's calculating what the rate of the first control, subject to 1.5 metres head, is going to be, and then also just check to make up the difference using the second flow control. And if I click OK here, I can demonstrate this really well with the 100-year event. So what you'll see now is I've got the complex, so I've got the full behaviour, the cumulative behaviour of both flow controls working now. Now, if I have a look at my cover level and my invert level, I know that in the 100-year case, I'm going to cap my water level at cover. I'm not going to allow any flooding. So that's 2.172 metres if you do the maths on cover level minus invert level. And if I look at my table, then a depth of 2.2, so just a bit higher than that, is 71.7 litres per second. So when I go in to put in my 100-year depth now, what I need to be careful of is that I haven't already got a cumulative flow that's greater than the flow that I'm going to try and restrict my complex flow control to. Otherwise it won't work. I'm already allowing enough flow through flow control number 1 and flow control number 2 that a third flow control is completely redundant, and actually I won't be able to achieve it. So in this case though, I know that I've got 79.9 litres per second, so I have got enough of a difference to be able to implement a third control, and I can put that height in here. If I didn't, say if I was going to restrict myself to say 60 litres per second in the 100-year event, if I click Solve now, you'll see that at 2.172 we've already exceeded 60 litres per second from our first two controls. So what MicroDrainage will do is it will warn you about this, and here you go, it's been unable to solve for flow control number 3. Doesn't make sense to have this extra flow control. It's not achieving what I need to do. So this is maybe where I might need to start looking at a series-based approach rather than a parallel approach in order to be able to control this. So I'm going to say OK, and actually I'll set this back to being my correct rate, so 79.9, and Solve. And what you'll see MicroDrainage is doing is it's changing the invert level of each control to kick in, if you like, at the point or the maximum head level from the previous one as well. So it's saying, well, we're going to go up to 1.5 and we'll only use the first two flow controls, but beyond that, we're going to then start using the third one. So this is how we go about doing the design of the complex flow control. It's all about opening this up and using our cumulative head and cumulative flow relationship. Just having an understanding of making sure that that is going to work and is appropriate when we add each control in. So I'll say OK to this, and you can see it's updated. This is now my cumulative behaviour. If we look at this in between 2 and 2.2, we can see we actually get that 79.9 correctly situated in the behaviour. So I can be confident that as long as I now control the water level in each one of the 1, 30 and 100-year storm events to hit those heads or not exceed those head levels, then I will have been able to meet my discharge requirements using my complex flow control. If we have a look at the form, you'll see as well, I've also got some smart annotations on the drawing here. It's updated to show me that there is now online complex control located within this chamber. What I'm going to do now for the design of the storage structures could be the process that Chris mentioned of iteratively going and opening up and sizing and having to balance this, so balancing the shape of my pond to make sure that I hit those cover levels or don't exceed those different head levels that I've specified already. And this can often be quite sort of the complicated and scary bit of complex flow control design, getting the two working in tandem, the piece of storage and the flow control. But alternatively, I've got the CASDEF module option available to me within MicroDrainage. So what I can do is I can use CASDEF. For those of you that haven't come across it, it's an automated, optimized tool that will go about adding storage or upsizing pipes within the network, or even adding flow controls into the network to hit maximum water levels at various locations. So what I'm going to do is I'm just going to set up this to CASDEF to run from my 15-minute storms all the way to my one-day storm events. And I can use something called a CASDEF controller to tell the system where I want it to make certain changes and where I don't want it to do it. So this is a little bit like drainage design criteria and using those auto locks, except this time we're looking at it from a storage point of view and maximum water level. So what you'll see is I'm going to say no to modifying controls because I have designed my complex control and set that. I know that that control will now work. It's just a matter of being able to add appropriate storage into the network to prevent flooding now in that 100-year case. So at 1.022, this pipe, I'm going to expect it to add some storage. I'm actually going to give it carte blanche and say if there's a more appropriate location to add storage at, then you can do that. But crucially, I can set the level not to exceed at the upstream end of this pipe, which is the flow control chamber. So by editing the return period and changing the level not to exceed, I can actually hit different storage requirements and see how much storage I need to provide at different depths within the network. In this case, though, I can change this. I could say if we wanted it to sit maybe with 300 ml of water out of the cover level, then I could do that. But that doesn't make any sense because I've already specified that I'm only going to allow water to reach cover. So you'll see it's flagged in yellow for me, and I'm just going to move that back to the cover level. So having done this, I'm going to give CASDEF free rein of the network, so it can look at everything, and it can add storage where it finds it appropriate. And I'm now going to go and kick off a series of simulations. So much like the seasonal return period wizard, if you've come across that, I'm going to put in my return period here. My maximum water levels are all referring to cover levels, so it's the no flooding in the 100-year case that I've been told to design to here. I'll select my default set of durations, and again, I could pick my design criteria or analysis criteria here. I'm setting it up for the most stable possible run, so the smallest time step, taking that DTS off, switching DVD and inertia on. I could click finish. Now, what will happen is MicroDrainage will go away now. It will do all of its simulations, work out where there's flooding, and then iteratively do the upsizing and addition of storage into the network for me. Now, this process can take some time. If I were to go off, I've probably got 5 minutes here that it's going to be running through all of the different simulations. So to save us a little bit of time, what I've done already is before the webinar, I ran through this, and I've actually already created the CASDEF results in here. So CASDEF has gone through, it's added in some storage structures. So what I want to do now is I'm going to run, or I've run through for a whole host of different storms, and I'm going to look at each one of the return periods and just check to make sure that I have actually hit that discharge condition. So again, I can do this by looking at the 1 year. Yeah, less than my 21.3, so I can see it's optimized really well. I'm getting up to that level. And in my 30-year, yeah, 52.6, so a little bit of extra leeway in there compared to my 56.7. And then in my 100-year, I can see, yeah, I'm certainly less than my 79.9 litres per second. To save your eyes from having to go through all of these different results and go, oh, what does that mean, Max? We do actually have another process that you can use in here, which is on the results form. We've got, in the wizards, we've got an option to use a discharge wizard. So for those of you in an approving or a checking role, this is a really good one to run through whenever you see a model that's looking to achieve multiple discharge conditions. Again, you set up your rainfall and your durations and your return periods, and then here we can ask the MicroDrainage to do a check on the discharge rates. So it's going to run through, and I'm telling it the maximum allowable rate in my final pipe, so my outfall, for each selection. I could also include discharge volumes if I wanted to. In this case, I'm just going to do the rates. I'm going to assume we've already answered the volume question, hence we've been allowed multiple different discharge rates. And MicroDrainage will run away now, go off, solve for me those problems, and come back with a nice little report that will hopefully show me 3 big green ticks saying, yeah, well done, Max. You've been able to run all of those different simulations at the different return periods, and it's just doing that post-processing and analysis of the results automatically for me. in here. So whilst MicroDrainage goes away and has a look at this, I'm going to show you one final model as well, which is my Q-bar rate. So I went through and I did exactly the same exercise, but this time rather than using a complex flow control, I just used a single hydro rate with a design point of not exceeding the cover level and hitting my design flow. I ran through the same process of using CASDEF to size some storage structures within the network. And what I'm going to do is I'm going to open up another quick little form which is really useful, which is the volume summary static. And I can see here, this gives me a breakdown of the total amount of storage volume in my manholes, in my pipes, and also within the storage structures that were added to my network via CASDEF. So I can see here that I've got a total amount of storage of about 5,500 litres per second on site. And I'm just going to show you now that my other model is finished, we can have a look at a quick comparison in my multiple discharge rate. First of all, I'm going to do my discharge rate checks. You see some green ticks. I've managed to pass everything, so this is my nice little breakdown that's proving to me, yes, your post-development conditions have bettered my pre-development, and they've certainly not got any worse. And again, if I bring up the same form now, so my volume summary static, and do a quick comparison, you'll see on the right where I've been able to use multiple discharge controls, and I've been able to let CASDEF run off and do its sizing of the storage structures for me. It's come back, and the total amount of storage that I've been providing is about 900 meters cubed less. So really significant saving of storage within the site. You can see by the numbers, my pipes and my manholes are identical in both cases. It's purely the storage structure volumes that I've been able to play with. If you look at upstream of the flow control, significant reductions there compared to my Q-bar rate. So hopefully you've seen there some quick and easy ways to be able to implement flow control design. So what we'll do now is we'll just move back to a bit of a summary, but hopefully that was really useful. And now we'll see, give it a go, get in touch. We've always got our technical support team that you can raise any technical queries with, but hopefully that's been really useful. So summary points from myself, we can hit those multiple discharge rates and get a massive reduction in our storage volumes, which can be really beneficial, not only to you, but your clients as well. It doesn't have to be so complicated. We're using that complex flow control wizard and just working on cumulative depth and flow relationships within MicroDrainage, using those hydro breaks to really help me control the flow and get that small variation in flow rate for large differences of head, which makes life a lot easier as well. I also use CASDEF as well. And one point that I'm really glad that Chris raised as well was the management and maintenance plans when we're designing these flow controls. Often very overlooked, but certainly something that, again, I know Hydro will be able to talk to you in regards to that. So Chris, any comments from you in regards to what we've covered today?
No, I think it's hopefully what we've shown you today gives you, shows you the process that you go through, and it's a very replicable process across multiple models and multiple designs. So hopefully that answers a lot of queries and concerns that people have had and raised often.
Great stuff. So I think what we want to do now is we're just going to have one more poll question, and we'll see if we've done a good job or whether we're going to have to stay late in detention and see if we can run through it again. But hopefully you're all now feeling a little bit more confident in being able to have a little bit of a go at designing these complex flow controls. So we'll leave that open for a second. Well done, everybody. This is this is looking quite good for us at the minute. So we'll close that now, and we'll show you. Brilliant. Well done, Chris. Job done. I think a vast majority of people are looking a bit more confident now. And for those 7%, don't worry. The webinar's recorded. We can do it, or maybe we can have a chat with you separately as well. So thanks very much, everybody. Just a few last points from ourselves. As Innovyze, we will be running another webinar on the 30th of October, an introduction to MicroDrainage. So perhaps this one, certainly if you're getting involved in complex flow control design, maybe something that you're an experienced microdrainage modeler. But for those just starting out in the software, a great introduction webinar coming up to get you used to using microdrainage and what on earth it's all about. Bit of a drainage 101. I know, Chris, as well, you've got some webinars coming up and some events as well.
Yeah, so our next webinar is a highways webinar looking at treatment of runoff that comes off of highways. That's been held by my colleague Mark Goodger on the 14th of November. And then we're also attending the UK Highways Conference and the WEM Conference later on in November as well, so please feel free to come and visit us.
Yeah, so I think really sport for choice, but certainly come see us, come say hi, and we look forward to seeing you later. So without further ado, thank you ever so much for joining us today. I hope it's been a really useful webinar, and just our contact details as well if you'd like to get in touch. But thanks for stopping by and look forward to seeing you soon.